Okay, last time I told you, I started to tell you about three major new discoveries about light that all happened, one right after another in 1800 and 1801. And I made the point that no one had really done much on in the field of optics, studying light, since Newton. Newton had made his basic discoveries way back in the 1660s and published them at the beginning of the 18th century. And really for about 100 years, not too much else was discovered about light other than what Newton knew. But that changed quickly at the beginning of the 19th century. And the first major discovery was made by this famous astronomer, William Herschel. And I told you last time that Herschel wanted to study the sun, sunspots and solar activity and so on. And so he wanted to train his telescopes on the sun, but of course it's too bright. You can't look at the sun through a telescope. So he had to use darkening glass that cut out the vast majority of the light in order to make the image dim enough so you could actually look at it. And he noticed this very peculiar effect, that when he used a blue glass, so the image of the sun looked blue, and was dim enough for him to look at, then that was fine, and he could look at it, he didn't have a problem. But when he used a red glass, so that the image of the sun looked red, even though the light itself was just as dim as it had been in the blue case, it seemed like more heat came through, and his eyeball would heat up when he looked at the sun. So that gave Herschel an idea. If that happened to you, what would you do next? Any ideas? Not look at it. No, that's not a scientific thing to do. You want to find out why. What's going on? Why when the sun's image is red, does more heat come through versus when it's blue, even though the same amount of light seems to be coming through in the two cases? Now, well, this gave Herschel an idea. He knew from Newton that you could take sunlight and spread it out into a whole spectrum of colors, right? Newton was the first to do that, to show that ordinary sunlight consisted in all of the colors and that you could separate them with a prism. Well, Herschel got the idea, what if the different colors of light contain different amounts of heat? What if heat isn't distributed evenly among the colors? It doesn't seem to be, based on his initial observation, that his eyeball heats up when he looks at the red image and not when he looks at the blue image. So he has the idea, well, let me take sunlight, put it through a prism, spread it out into the color spectrum, and let it fall on several thermometers, and then see whether the temperature rises the same in all those thermometers or whether it goes up more, some colors heated up more than others. So, okay, this is Herschel's first idea. We call this 1A. He takes several thermometers, say mercury thermometers, and he puts sunlight through his prism and spreads the spreads the prism out say in this direction, so that say we have violet over here and red over here. And say green in the middle. I mean, this would be blue, this yellow. Okay, now, oh, and by the way, Herschel was careful here. He also put a thermometer way over here somewhere else in the room, so it couldn't possibly be hit by any of this light, so he had a control, right? So he knows what the room temperature is. Now, the results he saw were something like this. Let's say he shines the light on these thermometers and then he waits for 10 minutes. Okay, he sees the one in the violet end of the spectrum go up by, say, 1 degree. The one in the green part of the spectrum, say, goes up 2 degrees. And the one in the red goes up 4 degrees. And these are roughly the kind of results he got. So call this temperature increase after 10 minutes. Okay. Well, so now he's got a good explanation, right, for what was going on when he looked at the sun. I mean, obviously the red light has more heat in it. I mean, it makes the thermometer go up, 4 times as much as the violet light. Now, what would you do next? The really clever experiment comes next. Herschel has another idea. Neve, do you have? Okay. Well, it occurred to Herschel, I mean, as the location of the thermometer moves over to the red end, he saw a steady increase in the amount the temperature went up. So it occurred to him to ask, well, what will happen? And this is the second experiment, so you can call, suppose we can call this B. I'm going to keep my diagram though. It occurred to Herschel, well, what happens if I put a thermometer over here? Now there's no light that I can see over there, but it seemed odd to Herschel if he could move his thermometer, say, all the way over and get a steady increasing amount of heat all the way to the edge and then have it abruptly go to 0 as soon as he moved it another 1/4 inch, say. At least he thought it was worth trying. Well, what happens if I put the thermometer outside the red end of the spectrum? That's exactly what happened. It got even hotter. So when Herschel did it, he found that this thermometer that has no visible light shining on it at all, he waits his 10 minutes, goes up 6 degrees. Now, what does that mean? What would you conclude from that, Daniel?
There must be even smaller amounts of light that are not visible to the eye, but there must be these tiny or ultra, like fluorescent lights, like something that's so bright it appears white to us.
Oh, well, it doesn't even appear white. Okay, I mean, it doesn't even. For instance, if you darkened the room, okay, and you, I mean, if the light over here appeared white, you would at least see a bright spot there. You don't see anything. Now, but you're on the right track. It's what Herschel concludes from this is, well, the sun puts out all this light, okay, that when we put it through a prism like this, bends it at different angles and spreads it out, but only some of that light is actually visible to us. I mean, the way Herschel put it, well, our eyes are only built in such a way that they respond to a portion of the light that the sun actually puts out. Sun is putting out light that our eyes can't respond to. You know, maybe there's some other animal that can respond to this kind of light. Who knows? But we can't. So we don't see that light, but it's there nonetheless. And you can tell it's there because it's clearly transferring heat to the mercury in this thermometer and causing the temperature increase. And in fact, this light that we can't even see, that's beyond the red end of the spectrum, has even more heat in it, can transfer even more heat to the thermometer than the light we can see. And Herschel called this light, does anybody know the name? He called it infrared light. Yes?
If you moved it right till it got past the violet end, would it still like get lower and like go down?
Yeah, well, Herschel tried that. I mean, naturally, this is one of the, after you see this result, one of the other things you would try is putting a thermometer out here, seeing if you see something. Now, of course, you don't expect to see much, right? Because even the violet didn't give you much of a temperature increase. Herschel couldn't find anything out here. I mean, the thermometer didn't go up any significant amount. So basically, he got 0 out here. But this is certainly a very interesting discovery. I mean, up to this time, light had always just been thought of as the stuff we see. And now Herschel has shown, no, there's the sun puts out this whole spectrum of light that, and we see a portion of it, but there's light, at least on the far red end of the spectrum, that has real effects that we don't see. Okay. Now, shortly after Herschel, any questions on that? Okay. Shortly after Herschel did this and published his paper, it gave another scientist an idea. Oh, I was told not to use that. And so let me tell you about the next guy. So that was discovery number one. Next guy is an interesting guy, Johann Ritter. He's a German physicist who had a lot of crazy ideas that I'm not going to tell you about, but he did discover make a couple of very interesting and true discoveries.
Did he discover this in 1800 as well?
Exactly. Yeah, this was also 1800. So Ritter had two non-crazy ideas, and I'm going to tell you about one of them right now. Well, it had been known for some time that there was a chemical compound, silver nitrate, that when you shine light on it, I mean, it's ordinarily a white compound, and you can, for instance, put it in solution, put it in water, and soak a piece of paper in it, say. But then if you shine light on it, it will turn it dark. Okay, so it starts out white, but if you shine light on it, it darkens it. Okay, this had been known for almost 200 years at this point. Now, this was actually a discovery that was going to be key to starting to develop the field of photography. But that hadn't been done yet. But Ritter, after he read about Herschel's work, he got an idea. He said, well, if the different colors contain different amounts of heat, maybe they differ in this other respect too. Maybe they don't all darken the silver nitrate by the same amount. Maybe only some of the colors darken it more than others. And he decided to investigate this. So he did a very similar type of experiment to Herschel, except that rather than thermometers, what he's going to do is, instead of a thermometer, he's going to have a strip of paper that he has soaked in this silver nitrate solution. Okay, so he's going to have let me see. Say various strips of paper here. Well, I might as well make this a little more symmetrical. And then he's going to spread out his spectrum the way Herschel did before. Okay, these are paper soaked in silver nitrate. Obviously, he's doing this in a dark room, right? So he's let the sunlight in through one small hole. He's put it through a prism. He's spread out this spectrum. He's got his violet over here and his red over here. And what does he see? Well, what he sees is that on the red side of the spectrum, the the silver nitrate doesn't darken as much and darkens more slowly. So this, say if he waits for a few minutes, this one, the red, the strip of paper in the red end of the spectrum darkens the least. And then this one at the violet end of the spectrum darkens the fastest.
Can
Sorry.
you look into the infrared section as well of light? Or?
Yeah, I mean he got this idea from Herschel, right? So he's just going to keep going now, do it the way Herschel did it. Now, when he does the step 2 of this experiment now, and he puts another strip out here, and another strip there, what do you suppose is going to happen? Yeah, what he finds is now that the strip that he places outside the violet end of the spectrum darkens fastest. I mean, even faster than the strip that was in the violet light. And the one that he places over here in the infrared light now darkens the even slower than the red, or not at all. I forget what his results were. But it's he gets very little response over here, and maximum response outside the violet end of the spectrum. Daniel.
So you decided to call that infrablue? Violet?
No, he actually calls it ultraviolet. Ultra meaning I think it's the Latin term for beyond. So it's the light beyond violet. So now we're completing this picture of light, this new concept of light, really, because, as I said, light was always just identified with what we could see, and now it's a spectrum that, scientists realize that sunlight consists of this whole vast spectrum, a portion of which we can see. Okay, so it really, the concept of light has changed. Yeah. Okay. See, all that's pretty simple. Wouldn't it be nice if there were experiments that were that simple today, where we could still make major discoveries like that? Maybe there are. People just haven't thought of doing experiments yet. Okay, now The third guy that I want to tell you about was an interesting guy, Thomas Young, Englishman, and the experiment that I'm going to tell you about, he first published in 1801. Sorry.
Did he read Ritter's and
Yeah, he was familiar with both Herschel's work and Ritter's work, and I think that it did have some effect on his thinking about light. Daniel.
It really matters, but where did he discover this? Where was he?
Oh, I believe he was in London. I mean, he was English. Yeah, Herschel was English. Ritter was German. Yeah, I mean, I think. See, right now, we remember that even Newton, who discovered that white lights, regular sunlight, could be spread out in this spectrum of colors, because each color was bent at a slightly different angle as it passed through the glass prism. Okay. Well, obviously there's something different about each color. I mean, each color must have a different property that causes it to be bent at a slightly different angle, and so you can spread it out in a spectrum like that. But exactly what that property was, Newton didn't identify. Now it's obvious at this point, when Young is doing his work, that Herschel and Ritter have discovered that the light spectrum is even broader than people knew before, and it spreads out even more than people knew before. It's bent at different angles, depending on some property as yet to be discovered. So I think Young is at least partially motivated in his work to discover exactly what that property is. Why is the various portions of this light spectrum, why are they being bent at different angles and spread out this way? Okay, now Young was an amazing guy. It became obvious that he was really brilliant even when he was very young. He knew how to read at the age of 2. By the time he got to high school, he knew 10 languages. By the time he was 18 years old, he was already recognized as a, his reputation as a scholar was already well known. So, he was a remarkably brilliant guy. But one of the fields that he did work in was physics. He was also a doctor, and he did research into ancient cultures, and he knew one of the languages he knew was Sanskrit. He knew these ancient languages. So he was a busy guy, but one of the things he did was physics. And he became interested in investigating light. And did one of the most famous experiments on light in the whole history of science, which I'm going to tell you about in a minute. But first, I want to warm up to it by giving you some background information. And let's just start. So let's call this background to Young's experiment. Now let's say we have a well, let me do this a little different. Let's say we have a pool of water. Now we know, let's say that we have a, at this point here, we have a little paddle device that whacks the surface of the water at this point. Now it sends out a whole series of ripples. Okay? So it's making waves in our water pool. Now, let's say we put another little paddle next to it over here, below it. And we start that one whacking the surface of the water. Okay, that will create its own waves. And these two sets of waves, created by each of these little paddles that we're whacking the surface of the water with, will spread out and then combine in some way with each other, right? Now, last year, when I talked about Newton's optics, we talked a little bit about waves. And when waves combine, they can do so in two ways. Does anybody remember?
They can add to each other or partially like sort of cancel out.
Right, exactly, because if well, let's get back to this in a minute. But if you have so waves can add or subtract when they combine. See, there's two cases. If you have, say, if you combine combining in phase okay, that means that the troughs and the crests of the waves line up. So if you have a wave like this, and you have another wave where the crests and the troughs are in the same location. If you add these two waves, okay, you're going to get one bigger wave, right? Because the crests are going to add and give you a bigger amplitude, and then the down part of the wave, the troughs, they're going to add and give you a bigger down section of the total wave. Okay, so you can take in-phase waves, add them together, and get one big wave. But if the waves, but if you take two waves and combine them when they're out of phase, so the second case is combining what is called out of phase, where wave number one is like this, say. Wave number two is like that. If these two waves add, well, what's going to happen? You add this amplitude, okay, which is positive, to this one here, which is negative. They just cancel each other out. Daniel.
It'll be just a straight line.
Yeah, right. I mean, the waves will just wipe each other out. If you add two waves like this, you get nothing. Yes.
Would they have to be going straight into each other, or would they just have to cross each other?
Well, they can, yeah, if they just cross each other, I'll get back to, for instance, those water waves that I was creating earlier. That's exactly what happens. Yeah, okay, so everybody's got these diagrams, know what they mean.
Didn't we do something like this last year?
Yeah, we did. We did with Newton's ring experiments. When I was doing Newton's optics, we talked about this kind of wave interference and how waves can combine in these in phase and out of phase. Now, okay, so let's get back to my two paddles whacking the surface of the water here and creating these waves. Now let's say that we have these paddles going in sync. So they both hit the water at the same time, all the time. Now, they're going to be creating waves that travel through the water at the same speed. And let's say we've got them whacking against the water with the same force too. So they're creating waves that are the same size. Okay, so the same size waves going at the same speed through the water. They're in sync. So at any point out here in the pool that is, for instance, the same distance from the two paddles, okay, how are the waves going to add? Neat. Right. They're going to add in phase, because if you're the same distance away from both of the paddles, and they're creating these two waves that are in sync, well, they're still going to be in sync if, at a point where you're the same distance away from the two sources. So any place along this line that is equidistant between the two paddles, okay, any place along there, you're going to get maximum amplitude of wave, because the two waves are going to add. So you're going to get maximum crests and maximum troughs. Okay, now, what if at some other location, though, let's pick a spot where, I don't know, let's say here, where the the distance to, say, this paddle is exactly half a wavelength less, well, I don't know where it would be. Let's pick it there. Let's say the distance to this paddle, let's call it D1, and the distance to this other paddle we'll call D2. Now what will happen, and let's say that this this distance here between the crests, the two different crests of successive waves, we'll call that lambda. That's the wavelength. That's called the wavelength of this water wave that we're creating with the paddle. Okay, so from one crest to the next crest is the wavelength.
What is that called?
Oh, this is a Greek, this is standard in physics to call a wavelength lambda. It's a Greek letter. So the now, what will happen? Let me ask you this. Probably, I don't know whether this is an easy question or not. What will happen if D1 minus D2, in other words, the difference in the two distances between this point I've picked and these two paddles, what will happen if that distance is half a wavelength? Neve?
The waves will hit each other out of phase.
Yeah, exactly, they will. They'll hit each other out of phase because if, I mean, this wave from, say, this paddle that's closest to this point that I've picked, okay, it's going to go through this distance D1, and it's going to be, I mean, who knows where it'll be in its phase. Let's say it's at a high point, at a crest. Okay, well, what will this one from the second paddle be? Well, it's gone through, after it goes through a distance, D1, okay, it will also be at a crest. But then it has to go an extra half a wavelength beyond that. Well, a half a wavelength beyond a crest is a trough, right? I mean, if you have a here's your wave. And I said, this is my wavelength from crest to crest. Well, half of a wavelength is from crest to trough, right? So if the wave from the first paddle is at a crest at this point, then the wave from the second paddle that has had to travel a half a wavelength further in distance has got to be at a trough. And so they have to cancel each other out. Now, in fact, this is exactly what you see when you actually do this in what physicists call a ripple tank. You can take two little paddles that create these waves in a pool, and then you can see, as the waves travel out, every place you can see lines radiating away from the two paddles where there's no waves at all. And those are the areas where you have this kind of out-of-phase combination where the waves are canceling each other. Okay, so I am going to make a connection between this and light, but that'll have to wait till this afternoon.